All right, so let's talk about data design and coming up with class diagrams, right? What are the process? What's the process? So let's consider just a very simple, trivial example where you have somebody wants to catalog their CD collection, right? So it feels like a fairly trivial exercise. We certainly want to be able to represent CDs. We want to represent maybe the tracks, right? And so maybe that's our schema, right? That we want to have titles and the release year for the CD, the band, the genre, and the tracks. It might be that each CD might have multiple tracks, right? So here we have the track might have the song title, the duration, the track number. They have a unique identifier for the track ID, and also has somehow it knows what CD it belongs to, right? And we start filling out our simple database, right? And as we're filling it out, we find out that our data representation doesn't allow us to answer some pretty basic things, right? As we start entering our data, it says, wait a minute, I have now the CD that is a best of CD with tracks from various CDs, right? So now you have a redundancy where one CD might have multiple titles, right, from multiple CDs that are already entered in there, right? They're already in the track. Should they be duplicated? Should I represent the same song multiple times? That's a problem that we would like to avoid, right? Having to represent the same song multiple times. What if I have the same exact content but in different order? Is there a way that I can represent that here? Right? It's the same song, but it's just in a different order, right? Our database doesn't allow us to capture that kind of thing, right? Where you might have exactly the same content but in a different order. There's no order in the track, right? Or that a CDs that grabs goes and grabs from multiple bands into a band per track. So our schema doesn't support that either. Or that it might be multiple genres. So our genre here, where we have a CD and it has a genre, it's not generic enough to have a CD that has multiple genres in one single CD. Or also performers in a band, right? There might be that folks in the same band might have gone and done something else on their own, right? Or joined some other bands and then come back, right? They're no longer part of that band, or they have their own band, right? So how do we capture that? Ideally, we don't want to start at the low level of the schema, right? Of the relationships of foreign keys, primary keys, and things like that. Instead, we like to think about this at a much higher level, and then decide what it is that we want to convert it into. Right? So we'll start at the class level, at a higher level, and then we'll decide what the corresponding tables might be at the relational representation. So in class diagrams, we use just a straight line as for implementing our relationships. We don't actually represent foreign keys and primary keys in class diagrams, right? The line itself is implicit. It is implied, right, that when you're going to generate this in a relational model, there will be a foreign key and a primary key, but you don't capture these things in the class diagrams, right? Because class diagrams are independent on how you're going to implement that relationship, right? Foreign keys and primary keys is just an implementation detail. Yes, that is how they implement the relationship. Right? So attributes, you're going to typically they're going to be corresponding to fields, right? And eventually these classes are going to be converted into tables, right? So we like to see how coming up with a class diagram, how that help us to generate our data model, our SQL data model. So here's where we want to reach, and we like to take you through a journey on how is it that we came up with this particular UML class diagram and the various decisions that might have gone on coming up with this layout of the data. So we have these pyramid students, departments, called these six different classes that are trying to model a small university. And you might say, well, where's the university? Right? Why is a university not represented in your data model? Right? So typically, we only represent things that we're going to be keeping track of, right? We're going to be keeping track of multiple permits, multiple students, multiple departments, multiple courses, multiple sections, multiple universities. We're not, right? We're not going to keep track of multiple universities. We are modeling the university, right? We're not modeling multiple universities, so there is no university class, right? This is the model for the university. This is the data that we're keeping track for the university. There is no university class. Yes? Same thing for our the project that you're going to be working on. There is no a project class or WAM class or Web Application Manager class, right? So here we identify that the student is participating in 3 relationships, one with the permit, one with the department, and one with the enrollment. And it has multiple different multiplicities. It's a 1 to an optional permit. The department can have multiple students, and the student can have multiple enrollments, can be enrolled in multiple sections, right? So we call these cardinalities. These annotations here tell us how many in that relationship are participating. For every 1 student, there can be many enrollments. For every 1 department, there might be many students participating in that relationship. And we call that cardinality. You need to represent cardinality and document it in your assignment. Okay, so make sure you have cardinality at each one of the extremes of each one of the classes. And there are different types of cardinality, and they're documented with an N and an M, N being the minimum number that participate, and M being, so it's a range, right? Where star denotes 0 or more, and star is just a short notation for 0 through star. 1 is a shorthand for 1 to 1, and these are the most common use, right? 1, star, and 0 or 1. So here's a one-to-many relationship. It's a very common one where you say that one of something can be related to many of others. Right? So one department can be associated to multiple students. Multiple students are related to the department. Notice that nowhere do we have primary keys and foreign keys, yes? But it is implied that when you're going to convert this into a relational schema, there will be a foreign key in the student that is related to a primary key in the department. It's implied. Right? But we don't actually document it in the UML class diagram. So I do not want to see any IDs or foreign keys or primary keys in the class diagram. Okay? And depending on how you look at it, from the departments to the students, we say that it's a one-to-many relationship. For both the students, you can say it's a many-to-one relationship, right? Depending on the direction that you look at the relationship. There could be also one-to-one, where it's a required, right? If you have a student, there must be a permit. If there's a permit, there must be a student that gets assigned to. We also use the jargon that if we know exactly how many are participating in the relationship, we'd say that that we are on the strong side of the relationship. Right? We know exactly how many are participating. We're not sure how many are participating, whether this one is optional, maybe 0, maybe 1, we don't know, right? Or it could be none or many. Or we say that's the weak side of the relationship, right, of the association. So we can say that this is a strong, weak relationship, or this might be a strong. Right? We know how many, or 2 to 5. That's also strong. Okay? It's just jargon. Or we might have a many-to-many, right? If we allow students to be enrolled in multiple departments, maybe they have a minor and a major, right? And so we want to say that's many-to-many. You know, one student could be. What this says is that if you give me one student, there might be multiple departments for that one student, or vice versa. If you give me one department, there might be multiple students for that one department. Right? This doesn't say that everybody is related to everybody. That's not what it's saying, right? If you fix one, then you know exactly which one's on the other side, or vice versa. If you give me one of them, not necessarily the same set, right? Not necessarily the same set. So we say that's a many-to-many. This is another case where there's no one-to-one implementation from this to relational schema, right? Because how would you do this? If this would be a one-to-many, That's easy, right? I have a foreign key and there's a primary key. But if I have a many-to-many, how would I do that? Would there be just foreign keys on both sides? That doesn't work, right? Because a foreign key only allows me to relate to a single instance on the other side. It doesn't allow me to relate one to multiple, right? So that wouldn't work, right? So the only way to reify this, to convert this and concrete this, is to have an additional table in between that would have foreign keys back to the original ones. Yes, right? So you can certainly draw this in UML, right? But there's no way to actually implement it in SQL without adding a new table. Right. So strong and strong annotations. Right. So star means that there might be 0, right? Or also 0 to 1. Also, it's also optional, meaning that it's not necessarily required. So you might have multiple instances that might be required, not required. So you could use that. Right. We say that's strong, weak, right? So here's just an enumeration of the various types of relationships and their names, right? So weak, strong, 0 to 1, or 0 to 1, or just 1, right? One to many. Okay, so weak. So those are just examples. All right, so ideally, what class diagrams allows us to do is to just visually look at these relationships. And just by looking at the class diagram, we can answer certain questions, right? And you say, okay, well, looking at the class diagram, we can say, give me a student, I can see who is enrolled in what section for what course. I can answer those questions, right? If you give me a student, I can tell you what course they're in, what sections they're in, right? What grade did they get for that particular section? I can also tell you, for one student, I can tell you all the courses that student is enrolled. Or if you give me the course, I can tell you all the students that are enrolled in that course. Also, what professor was teaching that particular section, right, for that particular course. Also, the average section size for a course. I can answer these questions, right? And presumably, these are the kinds of questions that were given to me in the requirements phase, and that's why I designed my class diagram that way. Yes, this is what drove the design in the first place, right? Right. So for instance, just to go through this real quick, I'm just highlighting here the cardinality here. And just give you examples that what they would look like in tables, right? So this would be a student might have these three students, Alice, Bob, and Chuck, and with different IDs. The enrollments they might have. It might say that these students over here are enrolled in these sections, and they when they completed that section, they got these grades, right? So these students are enrolled in these sections and got those grades, right? The sections, they have relationship with courses. Each course might have multiple sections. Notice that course 5610, there are actually two sections of 5610, and there's two sections of 4500, right? And we see that student 123, right, is enrolled in sections 3 to 1, which happens to be course 5610. So these values are basically referring to each other, right? That says that this 1, 2, 3 is referring. These are foreign keys that are referring to the student 1, 2, 3, saying that that one student is enrolled in these two different sections, right? And that's what the grades that they got. And these foreign keys of enrollments are pointing to the section that these three students, 1, 2, 3, 3, 4, 5, and 4, 5, 6, that all three are enrolled in section 5, 6, 7, course 4500. And this 4500 additionally refers to the 4500 or 5610 are referring to courses, right? For that particular section. And in turn, the courses are all being taught by the department, the CS department. So this just gives you an idea that you can navigate the data set, right, starting from one end, and just saying, right, well, these two are equal, allows me to navigate and from one table to the next, and traverse the data set in that fashion. So what class diagrams allows us to do is look at this at a high level. This is much easier to read than looking at thousands of records, right? Or different foreign keys and numbers and things like that. So this is an abstraction, right? This is an abstraction of something that is more concrete, right? And this allows us to talk about it at a very high level without talking about either Java or C# or SQL or anything, right? And be able to see ideally you would, if you want to change something or in the design phase, you would do them at the UML first, and then you would generate the data model, the relational data model. Right. So presumably there's a one-to-one, there's a mapping between class diagrams and relations. Classes become tables, attributes become fields, relations become foreign keys and primary keys. So let's look at this data model that we have here, where we have the schema is that we have CDs with IDs and titles and release year. We have tracks with track numbers, song titles, and duration. And we've added this additional one with lyrics and the author of those lyrics. Okay. One thing to note here is that track ID. Notice that from the notation here is that bold means that it's a key, right? Not necessarily primary or foreign key. It's a key. Underline means that it's a primary key, right? It uniquely identifies this record. And italic means that it's a foreign key, right? It's referring to something else. So notice that CDID here is a foreign key that refers to a particular CD. See that? Well, notice here lyrics. Lyrics has in particular. Notice that it's underlined and it's italic. See that? This says that it's a foreign key, but it's also a primary key, right? Meaning that it is referring to a track, okay? But it's also a primary key, meaning there can't be another one of these that can. Notice that a foreign key can repeat, right? I can have multiple tracks; they're all referring to the same CD. So this one is a foreign key, but I'm adding the constraint that it needs to be unique. Right? It's referring to that particular track. Okay? That if I want some lyric, it would be for a different track, not for the same track. Or there is a unique lyric for that particular song. Right? So I'm adding two constraints on it. So it's a one-to-one. Right? You give me one track, there's only one lyric to that track. Right? There can't be multiple lyrics for that track. Anyway. Yeah, so it's both a primary and a foreign key. Each track can have at most one lyric. So many tracks have one CD record. One lyric records has one exact track record. If there are no constraints, then presumably there can be 0 tracks for a given record. If there's no track, there's no lyrics. And having the foreign keys, presumably we have a many-to-one or one-to-many relationship, right? So if we look at some real data, we might take just an example of this. We might have multiple tracks, both referring to 2 different CDs, and you have lyrics referring to a specific track on a particular CD. So what we might do is that given that schema, we can infer what the UML class diagram would look like, right? Right. Notice that we've dropped all the primary keys, we've dropped all the foreign keys, and we have replaced them with just plain old lines. See that? It is implied that the track has a foreign key, the star, that's referring to some primary key, the 1. Right, that is represented by the CD, and we have the lyric. Oh, I'm sorry, it was a 0 to 1. So you might not have a lyric record for this, right? But if you have a lyric, it would be for that one track. Again, notice there are no foreign keys, no primary keys. We're only keeping track of the actual data, right? The track number, song title, and duration, right? So ideally, yes.
So how do you determine to like split those up? If the same ID can uniquely like determine if it's a track or a lyric? Why aren't the lyrics just part of the track?
Right. So if you would only have the lyric field, you could make that argument, right? It's only that one piece of data that I want to keep track of for that particular track, right? But the reason that we have this additional field, right, there's no way to keep both of them in a single value on the other one, right? Otherwise, you would have to redundantly have author multiple times in this record, right? So that's what extended. And actually, we have an example a little later. That we might agree that perhaps a better implementation would be to just put it here. Depending on how much is it that you want to keep track of. Same thing if you have a section and a professor is teaching that particular section. If you're only keeping track of the professor's username, then maybe you don't need a class, right? It could be just an attribute of the parent class, right? So again, it depends on what is that you want to keep track of, right? If you, from the professor, you want to keep track of additionally. Their office and and the office hours, blah blah blah. Then definitely we need an additional class to keep track of it. Okay? Again, the granularity and whether it's even worth keeping track of those things. That kind of walks you through a formal way of given a set of relational schema, what would be the class diagram, right? So given a set of tables that have foreign keys, so for any two tables that you keep track of, table 1 and table 2, we're going to just create one class for every table. Right? Give me all the tables. Each table gets a class. And then for any two tables, if there is a foreign key from one table going out to another table, then we're going to represent we're going to create an annotation, a line between them. But then we need to decide on whether annotate with a 1 or an optional or star. Right? If it's only a foreign key to a primary key, but the foreign key is not also a primary key, then it's a 1 and a star. Right? But if the foreign key is also a primary key, then it's a 0 to 1. And then all the attributes that are in each class become fields. Each field in the table become attributes in the class. Now, this algorithm doesn't take into account all possibilities like many to many, right? Where you have multiple, and so it only considers where you have one to many or one to optional, right? There are many other ways that you can represent data models that this particular algorithm does not take into account, and we'll come back to those a little later. So let's apply the same algorithm to this: student, departments, courses, sections, and role. Right? You have these. Presumably, this is the resulting class, right? Where you would first create 5 classes, right? So you have the student class, department, and role, section, course, and then you have the foreign keys. Presumably, major ID is a foreign key that goes out to the department. So there's a relation that goes there, right? But notice that the department ID is not also a foreign key, right? So it would be a one-to-many between the department and the student. Same thing between the department and the course. Notice that the course has a foreign key that goes to the department, but the department is not also a foreign key, so it would be a one-to-many, right, between department and course, right? One to the course. And then you have same thing enrollment. Enrollment has 2 foreign keys, one going out to the student, one going out to the section. But those student IDs is not also a foreign key, and the section ID is not also a foreign key. So that would be a one-to-many between these two. And notice that we drop all the foreign keys and primary keys since they're implied in the annotations, in the associations. Okay. So we're going to go the other way around, right? Of going from given a class diagram, we want to go to the schema side, right? So first, let's take a quick break, and we'll come back and we'll do that after the break.